Hi class, I have the schedule up here for this week, and we're working on hypothesis testing. So we're in Unit 4, and we are starting the basics of hypothesis testing, and we did a little bit of that in the last video, and then we also did some claims about a mean. And then this video is just to kind of add to this. We're going to add a test claim about a proportion. And I'm going to do another example and kind of review about hypothesis testing and mean and try to tie a lot of those definitions in there. Next week, you'll see we'll talk about two-sample testing. So two proportions, two means, independent or dependent pairs. And then the presentations, I'm not just sure yet exactly what's going to happen there, but I'll address that next week at some time. And then our exam will be here the week of the 6th. Okay, so let's go ahead and get started. Now, I'm still working on getting this set up. I would like to get a document cam soon where I can show you the problems that I have, and then do some work and show you where the information is coming from. But this will work also again. So what I want to do is switch over to my drawing tablet, which I'm kind of still getting used to. So my writing's not that great as it is, and this doesn't help. All right, so the first problem, again, this is a one sample mean test. Okay, so one sample mean t-test. And we're going to look at an example on doing that. And again, this is just one sample, and we're going to compare the results of that sample to some hypothesized value. So, which is what we're doing. Again, remember hypothesis testing. And this example has to deal with an assembly line. This information was reported in the Wall Street Journal. They said that the average assembly time for a Ford Taurus was 38 hours. Okay, so 38 hours. Okay, now we had done an example where we had a claim of gas mileage for a particular car, and it was that the average gas mileage was on the highway was 28 miles per gallon, and we said that we could collect a sample to test the claim of or the hypothesis of 28. And that's one way that you can use hypothesis testing. Now, this is going to be a little bit different. We're going to do the same thing, but it's how we talk about it concludes a little different. Now, this mean of 38 hours, in reality, we're not testing this. We're not going to collect a sample mean and see if it's close to this 38 because we think the 38 is incorrect. Okay. You can also use hypothesis testing, even though it's set up the same way. I'm going to take and draw a normal curve. This is our sampling distribution of the means, which is as n increases becomes more and more normal. But the 38 hours we're going to put right in the middle here. Okay. Now again, we're not testing to see if this is true. We kind of know that it's true. From the assembly times, they collect the data on how long it takes to assemble these Ford Tauruses, and that is correct. All right. So what are we doing? Well, what we're really doing is seeing if this 38 changes if we make a change to the assembly line. And we're going to use the same process. So what's going to happen is that Ford is going to go in and make some modifications to the assembly procedure and then see if this 38 changes, okay, based on that. So the original claim, again, we know is true, but then will that change? And we can kind of see that maybe through the sample. All right, so we go out and collect the sample. And for this sample, this is n equal to 47 cars. And they're going to take 47 cars and then after the modifications, measure on average how long it takes to assemble those cars. So the new average is 37.5, 37.5. Okay. And then the standard deviation, sample standard deviation is 1.2. Okay, so this is our sample data again. So we have sample data. And basically, we just want to see, does this sample, is this close enough to this number up here? And you might say initially, well, yeah, it's pretty close. So we'll just stick with this. That means those modifications didn't help. But then again, if we take a look at this, remember this is hours and this is hours. And you might say, well, you know what, a half an hour on an assembly line, that may be significant. So how much does it cost? And you know, I had read that a car company said it cost the company about $40,000 per minute to shut their assembly line down. So again, 40,000 per minute, it's a lot when you're talking about 30 minutes or 1.2 million. So yeah, that half hour is a pretty big deal. So now, does that mean that the modifications worked? Well, we need to see that difference could have occurred by chance because when we collected the data, when we collected the sample data, we really never expected it to come out exactly the same. So this sample mean, we didn't expect it to come out to be exact. So we knew it was going to be a little bit above, a little bit below. This one happened to be a little bit below, right? So it's below. And that's really what we're concerned about, right? We're concerned about, did the modifications decrease the assembly time? Because that's where we're saving money at. If we decrease the time, if it would have been above 38, well, we're making modifications to decrease it. Again, we don't want to take longer to. Now, we could have ran a two-tail test here. We really, wasn't our goal. Again, we could have said, well, if it's above, we want to know too. But we're assuming that there was a lot of testing involved and that they were pretty sure that it was going to be as good or less than what it was right now. So in that case, why do we care? Okay, first of all, why do we care? Well, a one-tailed test has more statistical power, okay, than a two-tailed test. In essence, it cuts that p-value in half because remember, p-value is area under the curve. So this is my critical region, right? I want to know how likely is it that this value, this group of 47 on average got an average of 37.5 or less. That's our p-value here. So we need to really find this. And if it's very unlikely, then that means that it's unlikely that things are the same, that there's some kind of difference after those modifications. And in this case, less than. So if we would have ran a two-tailed test, our p-value would end up being twice as much. And we don't, the p-values are probability of a type 1 error. Okay. So let me write that over here. The p-value again, area under the curve, but also is a probability of a type 1 error. So what's a type 1 error? Okay. Type 1 error is wrongfully rejecting the null hypothesis. Okay, so let's back up to here. So we have that the mean was 38, and again, we need to write that as a null hypothesis. So H sub 0 is that the mean is greater than or equal to 38. Okay, so you're saying, wait a minute, what did you just do there? Right? So why did I write this? Well, we want to go back to that idea of that the kind of proven, or we say that things are innocent until proven guilty. So with the conservative approach, we would start out by saying that after we run this hypothesis test, that we are going to be in this big area here. This is our null hypothesis support. Okay. So we're saying that when we take that sample, the sample is going to be around 38, what we hypothesize, or more. And then if that's not true, we get to reject that, which is what we want to do in this case. We want to be able to reject this. If we say somebody's innocent and we took them to trial, well, we really took them to trial because we thought they were guilty. And that's what we want. We want enough of evidence to reject the idea that they're innocent, which means they're guilty. So it's kind of backwards. This is where students struggle a little bit with that backwards kind of thinking. So we want to run a one-tailed test if possible, if it warrants running, then because of this right here. P-value is the probability of wrongfully rejecting the null hypothesis. Well, we don't want to wrongfully reject the null hypothesis. So our p-value, we want it to be as small as possible. Running a one-tailed test, well, at least cuts it in half, whatever it comes out to be. Okay. All right, so let's continue on. And we need to find the p-value. Okay, so see if I can get up the calculator here. All right. I don't think we need a full screen, so let's go ahead and put this in. And again, now, all right, we're running a one sample mean t-test. So let's go to stat, go over to tests, get a number 2, and we're going to hit enter. All right, so running a t-test. Again, the t-test we really should always run. The z-test is a theoretical. Even if the sample bias is very small, the t-test will adjust for it. So in this case, with a sample size of 47, there's a little bit of bias there, so we're still going to adjust and correctly use the t-test. All right, so stats. We got the stats over here. Is the stats or the statistics, and so all right. So the mean, the hypothesized mean is 38. The sample mean is 37.5. All right, so close, but are they statistically close? So standard deviation 1.2. 1.2. All right, so N is 47. And then let's go with the, what do we check here? Okay, so this first one here is if you ran a two-tailed test, less than left-tailed test. All right, there we go. Hit enter. And if we would have ran the right side here, shaded over here on the right, we would have said greater than. All right. So let's go with calculate. Oops. All right, there we go. So you can see the numbers, and I don't need to really rewrite those. You can see them right here. So we got a t, negative 2.856. So really what this means is we are 2.856, blah, blah, blah. We'll round that, negative 2.86 standard errors away from the middle here. So this distance from here to here, okay, this distance, right? Let me get that back up. All right. Well, you're saying that distance is 1/2. Well, yeah, it is. It's a half an hour. But in statistics, right, we're like talking about standard deviation. That's our unit of measure. And we are negative 2.86. The distance from here to here is 2.86 standard errors. Negative means one on the left, right? All right. So now here's the one we're looking for, p-value 0.003. So I'm going to write up here, p equal 0.003, right? This is the big number we got to remember. That's the one I'm concerned about because, again, p-value, what is it? Wrongfully rejecting them. So, I mean, if we have a big chance of being wrong, we're not going to take that chance, right? We want to be confident. We want to be, pretty certain about the claims we're going to make. If we make modifications to that assembly line, right, and they don't help, well, then all that time we lost making those modifications is kind of a waste of time and money and all that and so on. So it looks like, right? It looks like pretty good, 0.003. All right, well, what do we mean by pretty good? Well, what are we comparing that to? Well, remember that we have this alpha, and the standard is 5%. So normally you could see alpha at like 5%, 10%, 1%. We're going to set it at 5% this time. Just now remember that if p-value less than alpha, run reject h sub 0. So my p-value is 0.003. All right, we got that off the calculator. It is less than 0.05. Okay, p-value less than alpha, so we're going to reject. Right, h sub 0. H sub 0, there we go, is that the mean was greater than or equal to. So this we're saying was h sub 0, all this here. We're rejecting that, which means we're accepting this, that the really average number of hours it's taking to build those or assemble those four Tauruses is significantly less than 38. Okay. So we got evidence to be able to state that, which is kind of like a good thing, right, in this case. All right, so we got a lot of stuff in there, right? A lot of stuff in that one problem. All right, so let's go ahead and clear canvas. And let's go ahead and look at, yeah, this is a one proportions z-test. Okay, one proportion z-test. So one proportion, it's one sample, all right? One sample, again, one sample test. And you're going to have a sample proportion against a claimed proportion. Let's take a look at this example. Again, this is U.S. Department of Transportation National Highway Traffic Safety Administration reports. Okay, they report that 77%, so P equal to 0.77. 77% of all fatally injured automobile drivers were intoxicated. All right. So let's draw a curve here. All right, so we're going to put this in the middle again, 77. We're assuming that's correct, right? This is that case where we're not testing to see if this is correct. We know it is, right? We got this information. This is the data of all fatally injured automobile drivers, right? And it's from this National Safety Administration. So we're really, in a sense, not saying, but will this change? Will this significantly change if we make some changes to what's going on out there, right? So let's just say that uh, in existence, there's a certain type of advertisements that go on about drinking and driving. And I remember seeing things on TV where there would be a policeman standing there and there would be a car wrecked or something, and they would say, remember, don't drink and drive. It's against the law. Um, they would have commercials on the radio about, drinking and driving and how much it costs if you get caught. And so let's say that that's, the typical kind of thing. And then, but we want to change it. So here's some information in a particular county. And what they decided to do was some more billboard advertisements. And they had some things at the colleges. They had um, things involving like beer goggles. I don't know if you've ever heard of that, but you can drive and it simulates driving drunk, what it's like. And they have this full-fledged kind of awareness program for drunk drivers where they had, Uber drivers. If you were drunk and you took a taxi or something, they would pay for it, and so you wouldn't drive your own car. And so let's say, okay, well, let's say they go through and they spend a lot of money, and they want to see, well, does it work? And you say, okay, well, it's normally 77%, right? And we want to see if it doesn't make a difference. And so again, we're going to need some data here from the sample, right? We're going to need some sample data, but a little different. We don't need the mean and standard deviation for this one prop z test. We need to put in n, okay? So we need our sample size, and then we need our um, sample proportion, and that's it. All right, so before we put that up there, though, let's set up this null hypothesis again. So let's go h sub 0. Now, what we want to do, the whole idea of setting this up initially is, do we want to run a two-tail test, right tail, left tail, right? One tail test, either right or left. And it's a little tricky, and that's why, we think, okay, that shouldn't be that hard. Well, of course, the two-tail test is easy because we would just take this and put it exactly the same right here. P equal to 0.77, P equal to 0.77 would be our null hypothesis in a two-tail test. Okay, so that's the easy one. Now, let's say that we want to run a one-tail test. Well, does it warrant a one-tail? Well, yeah, because the whole idea of all this awareness for drunk driving is that we don't think it's going to make it worse. We don't think there's going to be more drunk driving going on, that it might not affect it. It might end up just being exactly 77. It's not going to end up being more probably. So we really believe it's going to be less. So we're hoping anyways that we're going to be over here somewhere on the left. Okay. So it sounds warranted, right? Sounds legit here. If we run a left tail test, we just need to find the area under the curve, right, to the left, based on our sample data. So what do I put here? I put h sub 0 is that p, well, greater than or equal to 0.77. Remember, the big part, greater than or equal to, here's 7, this is the equal to, here's the greater than part. This is going to be our alternative hypothesis that it's going to be less than, significantly less than, right? So, all right, so let's go and collect our data. And this was a pretty small sample. And they said that they had 27 automobile accidents, n equal 27. And the X, the number of drivers that were intoxicated, these are the fatalities. The numbers that were intoxicated were 15. Okay. All right. So let's see, what's our sample proportion then? P hat equal to 15 divided by 27 equal to, and what's that going to come out to be? 0.55. Does that come out to be 0.55, right? So let me just pull up the calculator. Where is that? Here it is. So I'm going to clear this, and 15 divided by 27, just to double check this. Yeah, 0.555. I guess we could say 0.56. We could round this one up. Okay. Okay, so 0.56. All right, now, and you might say right away, again, just kind of looking at that, we see the difference, right? 21%. That's a pretty big difference from there to there. But is it significantly different? And a lot of it has to, in this case, based on the sample size. That's a small sample for proportions. Reality, it would be nice if this thing were up in, 500, if we had, 1,000 or something. Our standard error would be much smaller. This is a little different than the means. The standard error for the proportions is based largely off of sample size. So we have to kind of remember that's an important thing. So a small sample size, there could be a lot of error in the results here. So we may need that big of a difference just to even get a little bit of statistical significance here. All right, so let's go ahead into the calculator again. Let's go over to the calculator, and I'm going to clear that. And stat test. And then we need to get down to number 5 here. One prop z-test, one proportion z-test. Okay, and then I'm going to hit enter. And you'll notice that they have p sub 0. Let's go for p sub 0. That's 0.77. X is 15. N, again, 27. And again, that's showing a left tail test. Remember, this is for two tail. And that's for left and right. Left side shaded on the left, shaded on the right. All right, so it looks good. All right, calculate. And we got our hypothesis test value. So the Z test. Now, why is it not a T? Well, the calculator is a little inconsistent, but the reality of it is they would expect the proportions test to be much larger than this because of the possibility of error. And once you get into a really large sample size, the Z test and the T test are pretty much identical. But the reality is we should really be adjusting here. But this is all we got right now. So we're going to do one prop Z test. And this negative means we're on the left side. So we're to the left of the middle. Right? And 2.65, right? So we're 2.65 standard errors, right, from here to here. 21%, right? But in terms of statistics, remember, more than 2 standard errors is a lot. So we got this 2.64 standard. That's kind of getting out there. We expect our p-value would be small in that case. Well, let's see what we got. 0.004, right? So 0.004 is our p-value. Right. And that's our important number there, right? That's kind of how we base our decision. Remember that if p is less than alpha, and I didn't put an alpha up here again, and really that should always be set up before you collect your data. But I'm going to just, again, throw it in here. By default, I'm going to put 5%. I think that's good enough for now. So again, remember, if p less than alpha, reject h sub 0. So p 0.004 less than 0.05. All right, we can make this up on 5, 10%. That's still less than all of them, so we're pretty happy with that. So we are going to reject, right, h sub 0. So we look up here, what was h sub 0? Is that the proportion of fatalities where the driver was intoxicated, right? Was greater than, going to be greater than or equal to 77% after we did this extra awareness program. We kind of wanted it to be less, right? That's why we spent all that money. And we're rejecting that it's the same or worse. We are saying that we have support that it is less than 77%, right? Which would be our alternative hypothesis. So we do have statistical support, and that's what that rejection is saying. That is rejecting the original claim of this stuff. And now we're down here in this region of rejection. Okay, so proportions again, very similar. The one thing I want to remind you is in these calculators, the TI-84 calculator X, if you put a decimal in here, you're going to get an error. And also that if you sometimes aren't given X, sometimes you're given a proportion. So if I would have been given a point, let's say that they said, oh, well, our sample proportion is 0.5555, right? Remember, it was like a bunch of fives. And that our sample size was 27, right? Let's say that's what was given, and p hat, right, sample proportion. Then x equals n times p, okay? So you'd multiply 27, these two numbers together, times 0.5555. So if we do that, clear this up, 27 times 0.555, yeah, and enter, and see we get 15, right? That's what x was. X was 15. So yeah, so x would be equal to 15. So really what we're finding there, and again, if you kind of remember back to binomial distributions, how did we come up with the mean? We had to multiply n times x. So we're kind of finding the mean of a binomial distribution, right? And in this case, it's considered binomial because they were either intoxicated or not. That's how we're treating it. So, okay, so that's really it then for now for the one sample test. And then on the next video, I will talk about two sample means, independent and dependent, and then two sample proportion tests. And that'll be for next week. So until then, continue to work in my math lab, my stat lab, and uh, hopefully this will all work out well for you guys.